Okay, good morning, everybody. Hope you guys are doing well. I want to go over the word problems from Chapter 5, Section 3 today with you. You needed to complete 85 through 88 and then number 93. So let's take a look at those problems. So starting 85, 86, 87, and 88 all deal with the same problem. And I thought this was kind of interesting because, as I had previously stated when we first started discussing this section, the loudness of your music or vehicles or horns or all kinds of things that you can think of that make noise, which are called decibels, is actually it's used as on a logarithmic scale. So what that means is there's a relationship between in the decibels, beta is what they use in this problem, and then the intensity of the sound I in watts. So for number 85, they give you this equation, which is beta equals 10 log I, which is the intensity, over 10 to the negative 12th power. And so for number 85, they said use the properties of logarithms to write the formula in simpler form and determine the number of decibels of a sound with an intensity of 10 to the negative 6 watts per square meter. So let's start by reducing this formula into a little easier, more usable form here. So we're going to have beta equals, now you can see there's a 10 there, but we have a quotient here. So we're going to split this up and make this log of I minus, now the 10 needs to be in front of this log as well, log of 10 to the negative 12th. Now, there's not much we can do here, but this part over here, this second part that I just double underlined, that's log base 10 of 10 to the negative 12th. So the first thing we're going to do is we're going to bring this negative 12 down, and we're going to multiply that negative 10 out in front. So we're going to have log of I plus 120 log of 10. And log base 10, there's nothing written there, so it is a 10 of 10. That turns into 1. So our new formula that we end up getting is 10 times log of I plus 120. Now they asked us to determine the sound, the decibels, with an intensity of 10 to the negative 6 watts per square meter. So now in this formula, we need to figure out the decibels, which is our beta, by substituting in 10 log, and then we need to write in for I 10 to the negative 6th plus 120. Now going from there, we're going to utilize the power property again. We're going to bring that negative 6 down in front and multiply the 10, so it becomes negative 60 log of 10 plus 120. This turns into 1, and we're left with negative 60 plus 120, which is 60. So beta, in this case, which is your decibels, would be 60. Moving on to 86. 86 asked you to find the difference in loudness between an average office with an intensity of 1.26 times 10 to the negative 7th watts per square meter and a broadcast studio with an intensity of 3.16 times 10 to the negative 10th watts per square meter. Now, you could use the original formula they gave us, but the one that we solved for right here, and I'm not sure, did I lose it? There it is, sorry. This one right here is the formula that we're going to want to use. So 10 log I plus 120. So beta is equal to 10 log I plus 120. And so what we need to do is we need to actually find the decibels at each intensity and then subtract the two. So for the first one, we'll call this beta sub 1, and that's going to be for an office. That is going to be 10 log 1.26 times 10 to the negative 7th plus 120. And when you do that, Actually, before I get that answer, let's do the second one. So here's the second one. The second one, we'll call it beta sub 2, is going to be 10 log, and then the other intensity is 3.16 times 10 to the negative 10th plus 120. And so we're going to end up with two different betas. So typing those in your graphing calculator, for the first one, you would end up with 26 decibels. For the second one, you would end up, well, that's not true. Hold on. I apologize. I actually need to take a second and type this in. So give me 1 second. Okay, so after typing those in, what we end up with is for beta sub 1, we get a decibel level of 51 point, we'll say 00. For the second one, we end up with a decibel level of 24 point, it would be 996, so that would actually round it to 25. And so now, by subtracting those two, we're going to do 51 minus 25, and we will get 26. So there's your answer. That's the difference between a broadcast studio and an office. So moving on to number 87, says find the difference in loudness between a vacuum cleaner with an intensity of 10 to the negative fourths watts per square meter and rustling leaves with an intensity of 10 to the negative 11th. So once again, we got to go back and we got to utilize this formula here. Beta is 10 log I plus 120. So once again, beta equals 10 log I plus 120. So we're going to have two betas, the same as the last problem, and we're going to subtract the same. So we'll call this beta 1, and we have 10 log. The first intensity, vacuum, was 10 to the negative fourth plus 120. And the second beta, we'll call it beta sub 2, was 10 log 10 to the negative 11th plus 120. So give me 1 moment to type that in. Okay, so what we end up with the first one is we ended up with a decibel level of 80. The second one ended up with a decibel level of 10. And when we do 80 minus 10, we get 70. So the difference between the two would be 70 decibels. Moving on to number 88. 88 says you and your roommate are playing your stereos at the same time at the same intensity. How much louder is the music when both stereos are playing compared to just one stereo? Now, logically, you would think, okay, if the intensity is twice as loud, then the decibel level is going to be twice as loud. But logarithms don't quite work that way. So let's take a look. We have beta equals 10 log I plus 120. But in this case, the intensity, which is right here, has to be doubled. And we're going to make it 2i because there are two stereos now playing, not one. Now, how is this going to affect the decibel level? Well, it will not double the decibels. And here's how I can show it to you. The first thing I'm going to show you is that we're going to split this using the product property. So we're going to have 10 log of 2 plus 10 log of I plus 120. Now, the next thing we're going to do is we're going to regroup it. And so it's going to become 10 log I plus 120. So that's the original part of the formula. And then we have this plus 10 log 2. Now, this part is the extra. This, what I'm going to highlight here in pinkish purple, that's what the original formula was. But by inserting in the top purple part a 2 in there, we ended up with this extra part that I'm going to highlight in yellow. So 10 log 2 is the extra result of putting a 2 up top in the original formula. And so when you actually type 10 log 2 into your calculator, what you find out is that is equal to roughly 3 decibels. So by doubling the intensity, you're only going to get an increase of 3 decibels. Okay, now moving on to the last one. The last one is definitely tricky. It is number 93, and that problem is very similar to the planets problem that we talked about in the notes when we discussed the notes. And the formula that you need from that is, let's get this. This is number 93. The formula you need from that is natural log of y is equal to m natural log of x. And so that relates logarithmic data from one table to other. So it says galloping speed of animals. Four-legged animals run with 2 different types of motion, a trotting and galloping. An animal that is trotting has at least 1 foot on the ground at all times, whereas an animal that is galloping has all 4 feet off the ground at some point in its stride. The number of strides per minute which an animal breaks from a trot to a gallop depends on the weight of the animal. Using the table to find a logarithmic equation that relates an animal's weight x in pounds and its lowest galloping speed y in strides per minute. So what we actually have to do is we've got to create a new table. So we have this weight, and we have these, it's 25, 35, 50, 75, 500, and 1,000. And then we had, that's our x. And then we had, I'm going to leave an extra column here because we're going to do natural log of x. And then we had our galloping speed. I'm going to put GS for galloping speed. And that's our y. And then we're going to take natural log of y. And so we had 191.5. We had 182.7. We had 173.8. We had 164.2. And we had 125.9. And then 114.2. Now what we actually have to do is we need to take each one of those numbers. They said they're related via a logarithmic equation. So we have to take each one of those numbers, and we need to take the natural log of each of those numbers to come up with a new data table. Now I'm going to save you the time in doing that, and I'm going to do it for you here real quick. So the natural log of x is 3.2, then we're going to have 3.6 roughly, then we're going to have 3.9, and then we're going to have 4.3, and then we're going to have 6.2, and then 6.9. This one right here, the natural log of y is going to be 5.3. Then we're going to have 5.2. We're going to have we're going to have to call that 2 as well. 5.3, 5.2, 5. I'm going to call this 1.5 just because, and then 5.1, and then 4.8, and then 4.7. All right, now what we need to do is we need to find this m right here, and that m is going to be the slope between 2 of these ordered pairs that we obtained using the natural log of x and then the natural log of y. So you really can pick any of the 2 ordered pairs you want. I'm going to use, I don't know which one should we use. Let's use the first one and the last one. So we'll use this we'll call this this one right here, and then we'll use this one right here. Okay, so we have an ordered pair. The two ordered pairs we have are 3.2, comma 5.3. That's my x1 and my y1. And then my x2 and my y2 are going to be 6.9 and 4.7. And so now we're going to do y2 minus y1, y2 minus y1 over x2 minus x1. So y2 is 4.7 minus 5.3. And then we're going to have 6.9 minus 3.2. When we do that, we are going to end up with negative 0.6 on the top, and we're going to end up with 3.7 on the bottom. And when I divide negative 0.6 divided by 3.7, I get a slope of negative 0.16 approximately. Now, that number might be off a little bit from what other resources you might have, is because I rounded all the natural log numbers to a tenth of a decimal point instead of going out to 3. But you can see that the slope here is negative 0.16. So, therefore, that gives us a slope, it gives us an equation, of natural log of y equals negative 0.16 natural log of x. Okay, there you go. Hopefully that made sense.